You are given points with an independent coordinate x and a dependent coordinate y. If you do scatter plot, it looks like there's a linear dependency between the points, so you can draw a linear line. In other words, you can express y as m times x, with m being the slope of the linear function. This also means that you could draw this triangle with 1 in x direction and m in y direction. But how do you obtain the m from the data that you have? Welcome to this video where we will look at linear regression from a probabilistic perspective. Hi and welcome to this new video. We'll first start by looking at the directed graphical model for a linear regression, and then we will use the maximum likelihood method in order to determine the least squares problem, which defines an optimization for the slope m, and then we will derive the analytic solution in this simple univariate case. And in the end, we will make a quick demo in Python. Let us first start by assessing what we have. We are given these orange points here that have a coordinate in x and a coordinate in y, and we consider x as the independent variable and y as a dependent variable. So let's look at that in terms of a directed graphical model. So we have a coordinate x, and since it is an independent coordinate, I will use this square notation because it is not probabilistic in our simple scenario here. And in there we have the random variable x, and I will give it the subscript I in order to denote the ith point. You could take, for instance, this point here, which would have the coordinate x8, so the 8th entry in our data, and it has correspondingly also a y coordinate, which would be the 8th entry. And here we have a bunch of them, let's say for instance 100 points. And this x is associated with a y. And this y is now considered probabilistic, so I will use the circle notation and also have the yi. And then there is an arrow connecting the xi to the yi, since the xi is causing the yi or is associated with it. And then we will use a plate notation in order to say that we have n of those points or n of those connections, because we have n independent data points. And the big question is now, where does the probability come in? And the idea is that the spreading of the y points based on x is given by a normal distribution. So let me note that down. I will use some quotation marks here. So the spreading or the distribution, let's say the distribution of y given x is a normal distribution. And that is an assumption that we make here, but it is an assumption that you will often find when you derive these least squares losses. And the parameters of a normal distribution are its mean mu and its standard deviation sigma. And you can think of this in the following way, that if we have a certain x position, so for the sake of argument, let us take this x position, and then we want to associate the corresponding y position with a distribution. So something like this here, so that we have a distribution which peak is on the line that we want to find, and then it has some standard deviation. Based on that, we can explain why the data is spreading around this linear line, because in real life we don't observe data which directly lies on that line. So we have the standard deviation which enters our distribution here. This standard deviation is sigma, and for the sake of argument we will assume it is given and fixed. And then we also have the mu position. And now the big idea of a linear regression model is that we don't have a fixed mu, but we have a mu dependent on x. So we have another variable that enters the probabilistic node here, and that's m, that's the slope of our linear function. And then we can say that yi is distributed according to a normal distribution over yi with the mu given by m times xi and the sigma or the standard deviation or variance, if you want to square it, which is also here. And that's the key part here, that the mu position is based on x. So when we are at a different x position, so let me also indicate that here. So if we are at that x position, we would expect the normal distribution to be something like this. And the key is that the sigma, which is defining the normal distribution, is identical in both cases. So it has the same spreading in this y direction here. So let me also indicate that here. But the mu, so where it is centered around, this will always be on the linear function that we want to find. And based on that, we can then recall the normal distribution, which is given in the following way. So we now have a probabilistic distribution over yi, so the ith sample from our data set, given xi and mu and sigma, which is going to be 1 over the square root of 2 pi sigma squared times the exponential of minus 1 over 2 sigma, and then multiplied with yi minus m times xi in brackets squared. And here again, we know that this is the mu, so this is where our normal distribution would be centered around. And now we are interested in the likelihood of our data. So the likelihood of our data, and recall the data is nothing else as a collection of x and y positions. So D is kind of an set which contains an x0 and a y0, which will be the 0th point. Then it will have an x1 and a y1 for the first point, and so on and so forth, all the way to n-1 and yn-1. It's kind of because I use a 0-based indexing. If you have a 1-based indexing, then it goes to n, and in total we will have n samples. Let's say, for instance, 100 data points. And then this likelihood is given under the assumption of an IID dataset, which we are doing here. And then it is given as the product from I0 to capital N-1, or in other words, the product over all the data points that we have. And then we query our distribution at the given points that we have. So we say capital Yi is lowercase yi, so the random variate that we observe, given that xi is the random variable that we observe under m and sigma. And then we basically have everything fixed except of m, since sigma is known in our assumption here. So in essence, this likelihood will be a function on m. Either way, let us express that, and then we get the likelihood of the data set will be the product from I0 to capital N-1 over 1 over the square root of 2 pi sigma squared times the exponential of minus 1 over 2 sigma, and then lowercase yi minus m times lowercase xi in brackets squared. And then let us simplify this. So first we have a product here consisting of the normalization and then this exponential term. So we can apply the product separately. So we kind of have the product over this. So let me first do I from 0 to n-1 over the normalization. So 2 pi sigma squared. Let me apply a bracket here, and maybe some more brackets here. And then we have another bracket equation with a product from I0 to n-1 over the exponential of minus 1 over 2 sigma, and then yi minus m times xi in brackets squared. And then let's first evaluate this. If we have 1 over 2 times pi sigma squared and we multiply it by itself n times, this is nothing else than raising it to the nth power. So we are getting 1 over the square root of 2 pi sigma squared in brackets raised to the nth power, and then multiplied. And here we have the product of n times this exponential term with the corresponding exponent changed. And if we multiply these with each other, so we have exponent and then everything with 0 times exponent everything with 1 in there, you know that if we have a product of exponentials with the same basis, we can add up the exponents. So we get times exponential, and this is a common factor in all parts of the summation. So we have minus 1 over 2 sigma, and then we have a summation. So we basically turned our product into the summation here from I0 to capital N-1. And then we have this quadratic construction here that we can analyze. So then a closing bracket for the exponential. And this is our likelihood slightly simplified. And as in every maximum likelihood method derivation so far, we are rather interested in the log likelihood. So let us investigate the log likelihood. And in order to get the log likelihood, we apply the logarithm. And here I will use a lowercase l and say this is the logarithm of our found likelihood. And then we know the logarithm takes a product and turns it into a summation. So we have the sum of 1 over 2 pi sigma squared in brackets to the nth power plus, and then we have, well, the logarithm cancels with the exponential. So we are just getting down the expression that we have here. So let me, yes, take the minus sign, minus 1 over 2 sigma, and then the summation from I0 to capital N minus 1 over yi times mxi in brackets squared. So the big goal was, let me go back all the way to the top, and our big goal was to find this m. And for this, we assumed that the sigma was given. So the sigma is not an unknown. The only unknown or variable that we want to optimize over later is m. So then let's look at these two terms here. Since in the long goal, we want to do a maximum likelihood estimate. So our goal is to do the following, to say that m, and let's say star as the optimized value, is given as the arc maximum over all m of the log likelihood given based on the data or fixed on the data. And then this term here is just an additive value. So whatever m value we will find as part of the optimization, this value will always be constant. So we can ignore it, and it's also reasonable to do here. So we will ignore it. So essentially we can say that this one is equal up to an additive constant given this particular term minus 1 over 2 sigma, and then the summation from I0 to n minus 1. And then we have this quadratic construction here. And then we see that there is another term, which is the sigma here, which would not change. So you can think of it as a constant prefactor, and the value just lowers or increases the value of the log likelihood. So we can just take the proportional and we are still fine. And then we get this one is proportional to minus 1 over 2. We will keep the 2. That is kind of a smart choice, as we will see later. And then we keep our summation here. And then we have the classical expression here. And then we are almost at the least squares problem that you might have seen before. However, we also have this minus sign here. So we are still doing an maximization because we want to get the m which maximizes the likelihood. So which has the highest probability of being the one that we want to have according to our model. But we can also rephrase this as a minimization problem if we take out the minus sign. So in other words, we say that m star is the arc maximum over all m. And then we have this loss function, which we already have here. So I will just copy that down. So that's where it is. And then we can just, we can take away the minus and change this into a minimization problem. And then we have arc min over all m, and this one is then over 1/2, and then the summation from I0 to n minus 1, and then here we have our classical expression. And this is the least squares loss that we just found, and I'm pretty sure you've seen this once before. So in other words, and maybe also as and preliminary conclusion, the least squares loss arises as the maximum likelihood estimate when we have a Gaussian error assumption. So this is the maximum likelihood estimate, or it's not the estimate, it's the optimization problem, let's say under and let me put that in quotation mark, under a Gaussian error distribution, error is a little, maybe not the correct term here, but this is the distribution or the spreading of the data. So it's a distribution of the data away from the linear function that we want to find. Well, and that's now the optimization problem. Usually that's where derivations end, since often we have optimization problems that can't be solved analytically. But lucky for us here, this can actually be solved analytically, and that's amazing. So let me note that down. This can be solved analytically. And that's amazing because whenever we can find analytic solutions, this is actually nice. So maybe let me remove the tier here. This is nice because usually those are better behaved and run faster than using numerical optimization algorithms. But how do we find this? Well, this is classical calculus. We want to make a minimization, or in general an optimization over loss function. Then we just take the first derivative and set it to 0. For this, let me define this expression here as L hat, maybe to denote that it's not log likelihood because we removed the L, but in essence it is quite similar to that. And then let's take the derivative. So we do dl hat by dm, and then let me analyze what is going to happen. So first the derivative propagates over the 1/2, so it's not, it's just a constant here. And then it propagates over the summation because it's a linear operation. And then it applies to the bracket here. So we apply the chain rule. So first we take the outer derivative, which will yield 2 times whatever was inside of the brackets, multiplied with this term derived with respect to m, which will be minus xi. So in other words, we will have 1/2. And then we keep the summation from I0 to n-1. And then we first have the outer derivative, which is yi minus m times xi. And this one has to hold to 0 in order to be an extremum, which is what we're looking for. And of course, since we have the 2 in the exponent, we also get it in front of that. And now you also see the reason we kept the 2. This is just a convenience now because the 2 and the 2 cancels. Of course, you could have also ignored the 1/2, but here, well, let's stick to the way it's usually done in mathematics. And then let's multiply this out. And then we are getting, let me change the color here. And then we are getting the summation from I0 to capital N-1 over yi, or minus yi xi plus m times xi squared has to hold to 0. And then we can rearrange this by moving, well, let's say for instance this to the other side of the equation. And then essentially we're getting 2 summations. So we have a summation on the left-hand side, which will be this one here. So m times xi squared equals the summation from I0 to n-1 over yi xi. And well, then we can see that m does not have an index, so it is constant with respect to the summation. So we can move it in front of the summation. So maybe let me do that really cheatingly here. And then the m is here. And then we can just divide by this summation expression. And then finally, we find the arc minimum m. Maybe let's also call it m star. So we get a fraction, and in the numerator, we have the right-hand side. So the summation from I0 to n-1. And there we have yi xi. And then in the denominator, we get this expression. So the summation from I0 to n-1 and then xi squared. And this one is the analytic solution that we have. And it's quite amazing because we have access to the yi's and the xi's, and we just plug it into the formula, and then we get the slope, which is minimizing this maximum likelihood estimate. Be aware, of course, this is just for the univariate case. So this is for the univariate case. So this means that the xi is just a real variable. It can also be a vector. That's kind of like the extension of linear regression. We will see about that in a next video. And of course, we have a couple of assumptions. I just want to quickly summarize them. So first of all, we do a normal distribution. And then, of course, we also have this IID assumption. But the normal assumption is more crucial. And you also find linear regression models that use different kind of distribution. They are called general linear models. Certainly these are a little more difficult than what we have here, but this is what you commonly find as ordinary least squares when we have the normal distribution. In our case, this will be fine. Also take care we don't have any regularization, so there is no regularization. So our data should better be well behaved. That means without any outliers or those kind of things. You will also see in one of the next videos how we can incorporate regularization that kind of allows us to use more robust estimates, and there we will also use prior distributions over the variable m. Last but not least, let's take a quick look at a Python example. I've already loaded NumPy and matplotlib and activated the interactive mode of matplotlib. First, I want to create some artificial data. Let me note that down. So we will create some artificial data. So we will say x, which will be a vector of our x collections. And here I want to use numpy.random.rend for 30 points. The rend will give us uniformly distributed data between 0 and 1. This is just some arbitrary data I have here. And then we will have y being m times x. And here I want to have some m reference. So maybe let me note that down, that we have m ref is 0.3. And then y is m ref times x. And then we have x and y. And then we want to use the linear regression in order to determine m again. So let me first show you how this looks like. Here, these are points that are distributed in x kind of randomly or uniformly. And then correspondingly, we have this points that lie on this straight line, and we have the slope of 0.3. You see that if you go one to the right, it's 0.3 above. But this is not really difficult because they are already on a line. I will just create some noise by doing numpy.random.rend(n) for normally distributed data. And here I will go with 30 again. This is the shape of the array that we need, and multiply that with 0.1. And then I will say y is going to be y plus noise. And let's create another scatter plot to show you. And here, basically, we now have the orange points. So these are, based on the same x locations, but our points have been like augmented with a little bit of noise. And also be aware the noise that we chose is the normal distribution. So that kind of matches our assumption. So we had the assumption that our error or noise would have been normal anyways. But this is of course just for this artificial scenario here. Either way, let's now do the estimate. So m estimate is going to be the summation of x times y. So we do an element-wise multiplication with x and y. Then we have xi times yi, and then we sum over all the entries. And then we divide by np.sum of x element-wise to the power of 2. And then let's look at the m estimate, and here we see it's 0.33. That's really good. And our reference was 0.3. So we see we are a little bit away from that. That's of course because of our noise. In case of having like more data points, even with the same noise, we will approach these values, of course, under the assumption that we don't have any outliers. And that's this quick intro to the linear least squares problem that has this analytic solution. And we were looking at the simplest scenario possible with the univariate case here. And also a note why I say univariate again, because we don't have an intercept. So we are only looking at linear functions which go through the origin. When we look at multiple linear regression in the next videos, where x can be a vector, we can also use that in order to encode a regression problem which allows us to fit the intercept, which is also extremely handy, of course, because oftentimes you don't have data that goes through the origin. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. Thank you so much for watching this video. If you enjoyed that kind of content, then please subscribe to the channel. I have more videos like that on here, and you also find a great playlist with videos on probabilistic machine learning. And of course also stick around for the next videos where we go into more detail about what is linear regression and how can it be used. Here you will now see similar videos, and then I hope to see you in one of the next videos.